London? These are from London, so these are Thames Tideway boreholes. And these are, well, this one's 90 metres deep, the latest one's sort of 100 metres deep. And what we've been finding as we go up onto the various things like the Greenwich anticline, obviously the erosion surface is older and older into the chalk, and so you're getting more and more of the older chalk coming through at the base of the cores, which is beautiful because it's giving us, for the very first time ever, really detailed core logs right down through the whole of the Lewis chalk down to the New Pit chalk. And the New Pit chalk forms the top of the cliffs here. So we go down as far as the top end of this cliff, if you like, just here in London so far with drilling and really good core in central London, central East London. The core is brilliant and shows up all the marker beds, so that within the Lewis chalk we've got various clay seams and marl seams, and in this part of the section those clay seams and marl seams are volcanic ash beds. The chemistry shows them to be derived from just off-ridge volcanoes, so very similar to the sort of thing we're seeing from Iceland at the moment. Yeah, and there are a series of them which go all the way up here, and the Shoreham marls at the top of the Lewis chalk, up here somewhere, are also, one of them is also a volcanic ash bed. So we've got a series of them represented through the Lewis chalk. They're all in this section here. We might be able to dig them out and recognise them. And we've also got some very characteristic flints, what we call the Lewis tubular flints, which are fabulous, which you can trace everywhere. We get them in core under London. As soon as you drill through them, you know they're tubular flints. You couldn't be anything else because they have a certain structure to them, which we'll show you here. Yeah, so we've got these marker beds, which we can then pick up in core all the way under London and are present here, which brings out a point that Chris was making, you know, about fascies and beds being so continuous. How on earth is there any tectonics in between? Well, in the chalk we recognise it because as you go onto a structure, these beds get lost. So they condense out and disappear. And there various things happen. You get slumping and sliding associated with it. You get styles of fracturing associated with those events. Movements in the rock. So there's a whole series of things that we recognise in the chalk that happen at just certain stages of time, and when you look across Europe, they're the same stages of time everywhere. If you take it a bit further and look at things like the evolution of the Eastern Alps and the Carpathian Mountains, you're getting thrusts developed at the same time. And this big 84 million year event that we were talking about yesterday, producing the New Haven chalk in the Campanian, if you remember, the same event. Surprise, surprise, when's the maximum period of metamorphism in the alpine core in the northern Italy, in the Sagittarius zone, where you get the deepest, the plate is taken down to its deepest level. That's 84 million years dated, and then it comes up rapidly after that. And so you're getting a whole series of mega tectonic events related to that. If you look very widely around the globe, and go to places like where you've been working in Egypt and along the Syrian Arc fold belt, along the Dead Sea Rift, exactly the same dates. So it's there's some big stress fields. Well, I say the same dates within a stage because you can't date them all close to that.
This is all North Africa, isn't it?
It's all North Africa into Europe and affecting. So what we are seeing in the chalks is the effects of those same tectonic events. And if your plate has got ancient fractures and faults through it, exactly what John's talked about every time, you know, when they're talking to us about it, those are the planes along which movement are going to take place. And they recognise two phases of movement. One is the Cretaceous bit, the late Cretaceous bit, when all the stress fields switched and all your strike-slip fault systems switched direction, as Ziegler and many others have demonstrated over a long time right across Europe. That change took place at the beginning of the Upper Cretaceous. And so what we've seen from then on to the present day is the same broad stress field acting on Europe, on the European platform, but the stress is switching in direction. And
this is basically when coincident with the end of rifting.
Yes.
In the end of the main rifting phase
yes.
in Northwest Europe, when it switched from
That's
spin
right.
rift to
right.
post-rift situation.
Right.
Yes, where everything in all the big Brabants in the North Sea stopped.
That's right.
Stopped on. Began passively subsiding after that.
Yes.
Yeah.
Well, some of them what appears to have happened is there's several phases. Some are active compressional phases, and others are relaxational phases.
Yeah.
So the relaxational phases are what they call, we were talking about yesterday, flexural isostasy, which I thought was a lovely term. That was introduced by that Danish team.